I'll mute myself.
So once we are live, I would like to welcome everyone for today's seminar with Annica Black-Shaffer. We are very pleased to receive her. It's late at night in Europe, and she's here with us. So Annica is going to talk about new mechanisms and materials for odd frequency superconductivity. And during her talk, you will be free to either raise your hand or send a question into the chat box. If you are following us on the YouTube, you can also send your question there that we will read it for you. So Annica, the stage is yours. Thank you very much for accepting your invitation. So feel free to start.
Great. Well, thank you very much for that kind introduction, and thank you so much for having me here. I'd like to talk today about odd frequency superconductivity, which is something I worked on for a couple of years at this point. And this talk especially would like to focus on new materials where odd frequency superconductivity appears, and also new mechanisms for how we can generate it. But to get going, let's see if we can get this there. Maybe some of you are not at all familiar to odd frequency superconductivity, so I'm going to give a brief introduction of what is it and where and how do we find it. I'm then going to jump into some of our results that shows that this phenomenon is actually quite ubiquitous, especially in topological materials or materials with different bands or orbitals. So I'm going to talk about Weyl nodal loop semimetals and try to convince you that they really make very good, or even I would say optimal, odd frequency Josephson junctions. And then I'm going to spend the latter part of the talk talking about multiband systems, so systems that have multiple bands or orbitals close to the Fermi level, and show that this phenomenon actually, you can directly link the odd frequency pairing to Kerr effect in the Strontium Ruthenate superconductor. And it could even appear in conventional superconductors if you drive them with light. And feel free to interrupt me with questions during the talk. Okay, so let's get going on the introduction. Actually, sorry. I first would like to acknowledge, of course, the first people who did all the work. So the work on the Weyl semimetals have been done by postdoc Firebos and Paramita. The light-driven work has primarily been driven by Jorge. Johan and Thomas, two recently graduated PhD students, also been involved in our odd frequency work, as well as Andreas and Demalia. Lucia did work on Strontium Ruthenate. Chris and Dushka has also worked on multiband system. And of course, without external support, none of this would have been happening. And especially the odd frequency project have been funded by the ERC, or is funded. Okay, so with that, let's start with a brief introduction. What is odd frequency superconductivity, and where and how do we find it? Well, superconductivity is, as any other ordered states, very determined, or you get the properties of it by looking primarily at the symmetry of the order parameters, called the order parameter delta. And the order parameter for superconductivity is essentially the expectation value of forming a Cooper pair. So you take the creation annihilation operator of two electrons, and they have some quantum number alpha and beta, and you form a pair like this. So the symmetry of the Cooper pair is going to determine the symmetry of the order parameter. Now, the Cooper pair is a fermion, so it needs to obey Fermi-Dirac statistics. That means if the two electrons that you pair form a spin-singlet combination, well, for this combination to still fulfill Fermi-Dirac statistics, so it's odd when you exchange a particle, it needs to have a spatial dependence that is S-way, or even in space at least. So you get the spin-singlet S-way combination, which really is the conventional superconducting state. But if you say, okay, I would like to have a spin-triplet combination of the spins instead, either the mixed spin or the equal spin, well, then you have to have if there's no other quantum numbers, you have to have a spatial symmetry that is odd in space, so say P wave, so you get spin-triplet P wave. So this is very well known. But what you could do, in principle at least, I'm going to show you that it happens very frequently, say, okay, what happens if I form a Cooper pair where I pair the two electrons not at the same time? So they have an internal relative time difference, T. And if you have a relative time difference, well, you can Fourier transform and you get a frequency dependence. And that's why that's where the odd frequency, or the frequency part, is coming from that. Well, then it turns out that the Cooper pair symmetries will still have this oddness when you exchange all the quantum numbers. So say that you have an even time dependence, even in equivalently, even in frequency, well, then you can still have a spin singlet S wave, or for that matter, spin triplet P wave. But if you end up with something that's odd in the frequency or time domain, then all of a sudden you can have a spin triplet S wave, and that still fulfills the symmetry requirements of this Cooper pair for that to still be fermionic. Now, how does this work with sort of conventional BCS theory? Well, in conventional BCS theory, you simply look at expectation values that are formed at equal time. So even if you pair electron at T and T prime, you let T prime go against T prime goes to T, and you form expectation value at equal time. And that is, of course, always vanishing. The odd, you cannot have something that's odd in time if it's at the same time. So this is always even in frequency, even if it either doesn't have any frequency dependence, always even. If you want to have something that's odd in frequency, well, how would you quantify it? Well, one simple way to do that, if you want to work in the time domain, is to say, okay, I have something that's that is odd in frequency, but it's still easiest for us to measure things at equal time. So still want T go to T prime. And if you then take the time derivative of this, well, then the expectation value of the Cooper pair or equivalent to the anomalous Green's function, then it's only odd functions that have a finite derivative. I mean, you see it directly here. It's this odd function of a finite derivative at T equal to 0, but whereas even function always have a 0 derivative. So this derivative can become a very clear-cut signal that you have correlations that's odd in time or odd in frequency. So that's one way to quantify the odd frequency component. So this slide here shows a little tiny snapshot of the history of odd frequencies. So it really goes back to 1974 when Berezinski proposed a spin triplet S wave phase. So it was odd in frequency in helium-3, and then say 20 years later, it was taken up by several people who started looking at this in superconductors, both spin triplet S wave and spin triplet P wave states, and also later on in various heavy fermion compounds. Majorana fermions are, in fact, if you start pairing them, would always have an odd frequency dependence. I'm not going to go into that here in my talk, but that's sort of a contemporary subject as well. Most of these are complicated models. They, for example, you need a composite condensate, and there have also been raised questions about stability. For example, you get a paramagnetic Meissner effect that the superconductor even can attract magnetic field, and then naturally is problematic for the stability. So these are all in the bulk, and they're in the intrinsic phase. So you really have the odd frequency. The pairing gives you directly odd frequency. So as you see, it's a lot of interesting things here, but it could also possibly be questions around here. I'm not going to focus on that in this talk. Instead, I'm going to focus on system would actually have a conventional order parameters. It's not going to be a discussion as a system superconducting or not, but we're going to find odd frequency correlations in the material. So this would happen, as I'm going to show you, very often in heterostructures and also in multiband systems. And this is really what I'm going to focus on. And if you're interested to read a little bit more sort of general about this, there's two good RMP papers, both from 2005 and more lately from 2019, that really focus primarily on these sort of systems, where it's not an intrinsic phase, but you have still significant odd frequency correlations. Okay, so what is the most dominant, or I would say the traditional system where you find odd frequency? Well, I would say it's a SF interface. You take a spin singlet superconductor and you put it next to a ferromagnet. The spin singlet state, well, the spin singlet state doesn't want to live in the ferromagnet. It has a wrong spin configuration. So one would imagine that you don't really get Cooper pair penetrating the ferromagnet. But it turns out in many systems, it still do that. You still get a long-range proximity effect into the ferromagnet as if it wasn't even magnetic. And even in the diffusive limit when the ferromagnet is dirty. And the question is, how does that happen? And it turns out it happens because the spin-singlet S-wave superconductor gets transformed into a spin-triplet S-wave state that then has to be odd in frequency. You can show it mathematically too, but just by symmetry, it has to be odd in frequency. Now, the spin-triplet state can survive in the ferromagnet. It's S-wave, so it will survive in any diffusive limit. And this make it possible for it to have a long-range proximity effect in the F region. All right, so how can we understand a little bit how does this transformation happen? Well, one way to think about it is just to look at superconductivity in ferromagnets. So if you start with a ferromagnet that has a little bit of magnetic moment, but not so much, then you end up with a spin imbalance like this. So it turns out that you have two different Fermi surfaces. You have a minority state that has a smaller Fermi surface, and a majority is this red state. And you can quantify the difference in the Fermi momentum by just the vector q. So you get plus q half for the spin up and minus q half for the spin down. If you work out what this does to a spin-singlet state, is that the spin-singlet state now gets modulated by this q vector. And this modulation, this exponential modulation, we can write as a cosine and a sinus state. And this is the FFLO state you might know about. So this is, it gets a spin-singlet state that has a cosine modulation and a spin-triplet state that has a sinus modulation. And if you just plot how this behaves, it will look something like this. So we start with a spin-singlet superconductor on this side, and here we have various other material. So here, if we have just a normal metal, the spin-singlet state can just penetrate just fine in the normal metal. There's no magnetism in the system, so we never get spin-triplet superconductivity. If you have a weakly spin-polarized ferromagnet, while you have the spin-singlet state, it starts oscillating. These are these oscillations, cosine and sinus oscillations here, but rather weakly. I mean, the Q is small, so the oscillations are rather long range. If you have a stronger spin polarization, the Q is bigger and we get sharp oscillations. It wiggles a lot, and you even get a little bit of spin triplet penetrating into the superconductor. And if you have a very strong spin polarized ferromagnet, these oscillations can't survive. And you can see that either by Q being so big that it just oscillates to frequencies, it disappears, or you can also just see that this spin triplet state doesn't really like the ferromagnet very much either, right? Because it still has spin up and spin down, and it dies out. However, you do get it surviving actually a little bit in the superconductor. So the question is actually what happened in this very strong limit, and that is actually a limit where we have most odd frequency. And what you can do there is to say, how can I still get superconductivity in the strongly spin polarized ferromagnet? Well, if you have an interface here where you have the same spin polarization, well, then you cannot do anything. But if you have an interface where the spin polarization is in another direction, then all of a sudden you have two different directions for your spin to rotate. You can, for example, do it along the y-axis. So then you get a spin-singlet state that gets transformed into the spin triplet around y here. And then when it goes to the next interface, you change the polarization to the z direction, and the spin triplet along the y direction is then rewritten along the z direction. All of a sudden now you have a spin up Cooper pair, and that will survive here. So what this tells us that if you want to go to spin singlet to triplet, well, you can do the mixed triplet if you only have one magnetization direction, but you can go to the equal triplet if you have in general non-collinear magnetization. So you can, for example, have two different magnetic layers like we had here. You could also have spin-orbit coupling at the interface, or it could be a helical ferromagnet that rotates magnetic moment like this. But in all of these cases, you do go from a spin singlet state in the superconductor to a spin triplet state in the ferromagnet. And if it's diffusive, p-wave states should in general not survive, and it will be odd in frequency. What are the experimental signature for seeing this? Well, I already told you that there is a long-range proximity effect, even in diffusive F, we just have S-wave states. In some SF, many SF system will have zero energy peaks in the density of states that you can relate to the odd frequency dependence. It doesn't happen all the time, but it happens in many things. Many of these systems have a permanent Meissner effect that you can direct relate to the odd frequency correlations, though it doesn't quite happen all the time. And there's a number of other things I haven't listed either here. But again, I would say there's a reasonable large body of experience supporting you have odd frequency pairing in this SF junction. So therefore, I like to call this SF junction sort of the traditional odd frequency system. Okay, so that was just a short summary of odd frequency superconductivity. I was saying, well, traditional odd frequency, and the take-home message here really is that it comes because the order parameter, or actually the pair amplitude, becomes a dynamic quantity, but depends on t, and it's also reasonably hidden because it's just with relative t dependence. If you measure anything at equal time, this thing is going to disappear, but nonetheless, it is there if you keep the time dependence, and it's well established in SF structures where you get odd frequency spin triplet S-way superconductivity. I have colored here in gray other system. It's well established. It appears also in essence structure. So you have a superconductor next to a normal metal. Here there is no magnetism, so there will be no time reversal symmetry breaking, but you still can get some odd frequency spin singlet P wave state. And it's important to note here that it's odd in frequency. That doesn't actually mean it breaks time reversal symmetry, because it's a relative time difference. It's not the overall time reversal of time here. And you can even get an odd frequency spin triplet S-wave state if you have some spin orbital coupling in the system. But in the interest of time, I'm not covering those systems here. Because what I want to show is how we can actually optimize the odd frequency coupling. So before I talked about SF junction, I want to show you a system that we have worked on where you even get more odd frequency than in the traditional SF junction. And that is by utilizing Weyl nodal loop semimetals. And to just introduce that, let me start with the 2D Dirac materials. So the 2D Dirac materials, well, they position you in between the metal where you have a lot of particle hole excitation on one hand and an insulator on the other hand. So the Dirac material has a direct spectrum with a very limited phase space for particle hole excitation. So this is in 2 dimensions, but the typical example is graphene or the surface of a 3D topological insulator. But if you move to 3 dimension, so this Dirac cone can now live in 3 dimensions, then we can either have a direct semimetal or we can have a Weyl semimetal. So in Weyl semimetal, they have Weyl points, single points, where the valence and the conduction band meet. In the direct semimetal, this Dirac cone is the twofold DNA. Well, actually, the point is fourfold DNA. It's 2 valence band and 2 conduction bands meeting. Excuse me. So the difference between the Weyl and Dirac is just that the Dirac has twice as much DNRs at the point here. But one can also imagine materials, and it happens where this Dirac cone or the Weyl node, the Dirac node or the Weyl node get expanded. So instead of having single points, you form a whole loop or line where you have the Fermi element. So you get a nodal loop semimetal if it forms a line like this. And if that is non-degenerate, well, then we have a Weyl nodal loop semimetal. But you can also have a direct nodal loop semimetal if you have, say, spin DNRs or some other DNRs in the system. So what's so special about this material, and what is the property we're going to use here? Well, as you might know, in a Weyl semimetal, you have this Weyl cones and these points, and it always comes in pairs in materials. And if you take those 2 points or pairs of points and project them, and the surface in between them, you form a Fermi arc. So you form states of zero energy that forms an arc on the surface. If you have a loop in the material, you do the same thing. You take the loop and you project it on the surface. And there it's actually going to form a full flat drumhead surface state. So all the states within this region here are states sitting in zero energy. So you have a lot of zero energy states at the surface. And that, of course, means you have a big density of state peak at the surface. And if this is a Weyl nodal loop material, there's no degeneracy, so it's going to have the spin polarization here. So say on on the upper surface, you say you, for example, have a spin down polarization, and on the opposite surface, then you will have a spin up polarization. But you really have a short peak that are fully spin polarized on the surface. And here I list a few materials that like a few years ago were proposed to maybe be this way nodal loop in the metals. So you can maybe see already here where I'm going, that this is something that have a very strong spin polarization. So we wanted to model this material. And there's a few different models you can use at the simplest level. And here's probably the simplest model here, where sigma here is the matrix in spin space. So it means you have a rather strong spin-orbit coupling in the bulk in this material. There are more complicated models which add some features, and we also looked at those, but I'm going to present the result just for this particular model. And so you have some, so T is just overall energy scale. Alpha here sets the shape of your loop. So if alpha 1 is equal to alpha 2, it's a circle. And then you can also dope the material with some chemical potential, and that will simply decide, do you have a loop, or does the loop get inflated to a donut? So for example, if you won't be able to fine tune exactly at 0 filling, you get a donut from the surface instead. So if we take just this model and we make a slab of it, so we cut it in the C direction, the band structure looks like this. So these are the bulk bands. It's a finite slab, so we have a finite number of bands, and we get one band or two bands really, one on each surface that comes down and sits at 0. And this is a flat drumhead surface state. So if you look where this band is located, it's located on the surface, which we see here. So here is the peak. This is the first layer. It has spin down polarization, and in the last layer has a spin up polarization. Whereas the density of states in the bulk has this the spectrum you expect from coming up from a loop material. Yeah, so you have a fully spin polarized surface in this model. So then the question is, okay, so if I take this material, I take a slab of this material, so I have one surface that's spin up polarized and one that is spin down polarized, and I put it next to two superconductors. I want to make a Josephson junction out of this one, so they have a veil nodal loop material inside it. And I use conventional superconductors. So the superconductor spin singlet, the material is fully spin polarized. You would expect no Josephson effect in this material. So here's a structure we're thinking of. You take the veil nodal loop, you put two superconductors. So the question is, should you get the Josephson effect? Well, if you don't think or believe in non-frequency superconductivity, you wouldn't get anything in the system, because you have a fully spin polarized end here and a fully spin polarized up state here, and you put an extra spin singlet superconductor, you shouldn't be able to tunnel any spin singlet pairs in here. But since we worked a fair amount of odd frequency, superconductors said, okay, maybe this is like the SF junctions, and we can get spin triplet, conversion spin singlet to spin triplet state. So we set out to actually model the system. So we built a big lattice model with sites here. With hopping, we just model the superconductors like a conventional superconductor, the veil nodal loop with the Hamiltonian I showed you, and some hopping element here. And here's some typical parameters we use, but we generally swept the parameters to make sure the result was stable. So we looked at this, we calculated the Green's function based on the Hamiltonian, and then we got the anomalous part. So this is this F part here, which is directly proportional to that, with this, the pair amplitude. And we decompose this pair amplitude into the spin singlet S wave state. The spin triplet S wave state is going to be odd in frequency. And we also looked at P waves, but they're actually negligible in the system. It turns out that they are either prohibited by symmetry in each layer, or they are very small because they go in the direction of the junction. So they're very small. So I'm not going to show those. I'm just going to show these two because it's the only dominant ones we have in the system. And this is what it looks like. So here is, well, this is just the real part, but you can do the same plot for the imaginary part and it doesn't change. So this is the pair amplitude on the surface layer. So here we have the dashed one is a spin singlet state. So in the surface layer, actually, the very first layer is sitting next to the superconductor. The odd frequency, the spin singlet state does survive, but as soon as I go one layer into the material, it completely dies out. The dashed line here is completely dead, right? And I go even further in. I also have a spin down polarized state, the red one. And you see here, it's actually, here you see expressed as odd in frequency very clearly. And this state survives. This is the only one that kind of survives into the material. So the only thing that happens if you go even further into the material, you only have the spin triplet S-wave state, and it is odd in frequency. So here we see directly that the only thing that survives in this structure is a triplet S-wave state, and it has a spin down polarization, because this was a state. If I go back here, this was a state with the spin down polarization. If I had done the same for this surface, it would be in the up instead that survived. And we can even look a little bit how this compared to other materials and how they propagate into the materials. So here plot the amplitude or the pair amplitude as function of number of layers in the material. So the spin singlet here kind of dies out. And here's the spin triplet odd frequency state. And we see these are for different doping. So here's when you have a loop, and here where you have the donut, and we see it doesn't change a lot. So this system is reasonably insensitive to you don't have to fine tune the doping. And the question is, of course, okay, is this better or worse than other structures? Well, if we make the material in between the two superconducting constant a normal metal, you get conventional Josephson effect, and this is just the conventional effect, the spin singlet states surviving. We can also look at the traditional SF junctions. And now we make the structure, instead of having a veil nodal loop material inside, we have just a half metal. And if you have a half metal with no interface layer, the spin singlet dies out and nothing else is produced. This is a half metal with collinear structure. You don't have any proximity effect. This doesn't work as a Josephson junction. If you have a half metal with some additional interface magnetization that is in a different direction from in the bulk, so in the bulk it's in the C direction and the interface is in the X direction, you do get an odd frequency spin triplet state surviving. That's what I talked about before, but you see it's pretty small here compared to up here, and we try to really match sort of density of states and so other quantities here. So it really looks like this the nodal loop structure really have huge amount of odd frequency where you don't get even in the traditional odd frequency SF junctions. And that's all nice, but I'm showing you pair amplitude here. It's not really what you measure in the Josephson junctions. You measure currents. So we calculate the currents as well. So we plot the current as function of various parameters. We can drive this material. So we can drive it with chemical potential. We can change the order parameter in the contacts. We can also change the coupling between the veil material and the contacts. So the blue line is the veil nodal loop material. The dashed line is a normal Josephson junction, and the best SF junctions we can get is this yellow structures here. And as you see, this is a log scale. So the veil nodal loop material is actually much better in all of these plots. It's even better than the normal. It actually carry more current than a normal Josephson junction. So we actually get a huge current in the system. And it's entirely coming from odd frequency pairing because there's nothing else that survives in the structure. And we attribute this huge current, or you can show it in more detail, but we can understand it by saying, okay, so the superconductor sits next to this flat drumhead surface state. So superconductor sits next to a lot of states in the material it wants to tunnel into. So the tunnel coupling gets very good in this material. And that allows us to have a lot of Josephson current. And since the specific spin structure of the veil nodal loop material makes only odd frequency survive. So that's why we believe that these veil nodal loop materials are really optimal odd frequency Josephson junctions, because they have really an excellent way of, there's a lot of states here that can couple to the superconductor, and they have the type of spin structure that makes only odd frequency states to survive. So this is sort of, I think it becomes a version of the traditional SF junction, but that's much better. Generates a lot more odd frequency. Well, generates a lot more current, and it's all driven by odd frequency states. Okay, so now I would like to switch gears a little bit and talk about odd frequency that doesn't happen in heterostructure. So now I want to go into the bulk And the question, how do you generate odd frequency there? And I'm going to show you that this will happen essentially anytime you have multi-bands, you have multiple bands, as long as the bands interact with each other a little bit. So I'm going to first show you how this works in a very simple 2-band or 2-orbital model, and then apply this to both Strontium Ruthenate and when we drive a superconductor with light. So how does this work? Why do I get odd frequency here? Well, I'm going to start with spin-singlet SY pairing. Yeah, I can start with something else, but for simplicity, let's start with that. And I'm going to show that we actually get odd frequency spin-singlet SY pair in the bulk. And the trick here is when you have multiple bands and orbitals, you end up with an additional band index for your Cooper pair. So this alpha and beta variables here that I had before, they now are not just coding for spin and spatial parity, but they also will have to code for the band index or orbital indexes, if you will. So now you can be a spin singlet state, the S wave. And if this combination is odd in the band index, then it has to be odd in frequency. So you're sort of trading oddness in band with oddness in frequency. So you can have even frequency, even band, or you can odd frequency, odd band. So this work from a symmetry point of view, this is allowed. And of course, the question is, does it appear? So I'm going to show you how it appears. And one way to think about which sort of combinations you can have is to think of what could be called a spot rule. And spot, this SPOT symmetries has to be equal to -1. So S here is a spin state that can be even or odd, spin singlet, spin triplet, or spin singlet. The spatial parity S or PY, and now we have an orbital or band parity, can be even or odd, and then we have a time. And the conventional superconductor is, of course, a spin singlet S wave, even in orbital, where it doesn't even have an orbital index, and even in frequency. But now, as I said before, you can have spin singlet S wave, odd in orbital, and odd in frequency. So it becomes an odd equivalent of the conventional state. And of course, you can do many other combinations here, as long as spot is equal to -1. But I'm going to mainly focus on this yellow areas here, where we combine things with the simplest conventional superconductor, but we still get frequency correlations. Okay, so that shows what I showed before is it can appear. It's a layer of symmetry, and the question is, does it appear? And what do we need to do to get it appear? So let's start with a simple 2-band superconductor. So you have a band A and a band B with some kinetic energy, epsilon, A and B, and some pairing in both orbitals of delta A and delta B. This is at this point, it's two disconnected superconductors. But I can add a term that has an interband hybridization. So I'm going to say, okay, my band structure is not completely diagonal. I'm going to add a term that jumps between the two bands, so to have an interband hybridization. You can do this in different ways, but this is the simplest way to illustrate it. Okay, so now I can take this normal part and I can re-diagonalize it. So I get two new bands, C and D, and it's fully diagonal. But if I do that, then with this new basis, C and D, I get a slightly different pairing part. So I get intra-band pairing here, delta C and delta D, but it also gets some interband pairing, delta CD here. And the interband pairing is proportional to gamma, as you might guess, and it's also proportional to the difference in the two superconductors, delta B and delta A. So this is sort of the symmetry. If you thought about the interface before in the SF junction, introduces some symmetry break in the system. This is the sort of symmetry breaking you need in this multiband system. The two states that you started with can't be exactly the same. Then you will always have this interband pairing between the two bands. Okay, that's all fine. I haven't still shown you there's any odd frequency, but to do that, I really need to start looking at time-dependent quantities. So I can define a time-dependent expectation value. So I have here, well, here I changed T to tau, but anyways, it's still time-dependent. So a pair C and D, and it can even be an even combination, so even interband pairing, or it can be the odd with a minus sign. The even one, if you let tau go to 0, will be even in frequency and be even interband pairing. I can also let tau go to 0 with a minus sign here, but that's not so fun because then this is just by Pauli essentially just 0. So it doesn't work. But if I first take the time derivative of the odd combination with a minus sign, and then let tau go to 0, I actually can get something that's non-zero. And that will automatically be odd in frequency, and it will be odd in the interband pairing because it started with a minus sign here. So now the question is, can I get this term to appear? If I get this term to appear, I know I have odd frequency in my system. So let's just start with the simplest possible parameters. I'm going to have the same bands, and just where the parameters is just a minus of each other. I re-diagonalize with a delta. I have this interband hybridization. I get my new bands, and in fact, this is constructing such that the intra-band pairing is 0. I only have interband pairing, so that's why it's a little bit contrived, but it means that at least in this particular limit, the even interband pairing is just following the BCS equation. And the odd interband pairing defined with this derivative here, so we know it's odd, I have here. And that's just proportional to the even part times the interband scattering. And it's also an I here, and the I here is important because it means actually this state, even if it's odd in frequency, doesn't break time reversal symmetry, because time reversal symmetry requires a complex conjugation too. This was a very specific example. I can now tune, solve the same system numerically, but not with this very specific fine-tuned point. And it turns out I get odd frequency pairing as soon as I have a finite gamma. So if gamma is 0, I don't have anything. And as soon as this alpha parameters that I just have delta B over delta A is not 1. If it's 1, it's 0. But as soon as it's not 1, I get something that's finite. So this shows that this odd frequency interband pairing will always appear. It's going to be proportional. Well, in this case, it's proportional even to the even frequency state. So that was going through a derivation with time dependence. If you so well, you can do the same thing using Green's function, Feynman diagrams, and perturbation theory. So let me just flash out how that works as well, because maybe some of you are more familiar thinking about this system this way. So I'm going to start with the same Hamiltonian. This is still, again, the interband scattering that we need. And then I'm going to, again, I'm interested in the interband pairing. I'm also interested in the anomalous Green's function go between 1 and 2. So for example, I can start in band 1 with the anomalous part. I scatter, so this becomes my scattering event. And I move into band 2. So this would be F1 scattering and then G2, because I want to form an anomalous Green's function. I need to have the arrows going out in both ways. Or I can do the opposite process. So I have a G1 here and an F2 here. So this will be the two diagrams, and then this is F1, 2. And then you can actually, because this is a quadratic model, so we can solve this actually, and we can sum the diagrams to infinite order. And if you do that, and you look at the F1, 2, and you form the odd combination, so it's F1, 2 minus F2, 1, it looks like this. And you can form the even combination, it's just with the plus sign. And here you see directly the odd combination here is odd in frequency. This is what this omega here is, whereas the even here has an even contribution frequency, because this D here is actually frequency dependent, as you see here, but it's all even multiples of omega. So we get odd frequency pairing as soon as gamma is non-zero and delta 1 is not equal to delta 2. So you need to have hybridization and symmetry break. It's exactly the same as I showed you before with the time picture, but now I've done it with just summing Feynman diagrams. Okay, so this shows that this can appear in a multiband superconductor. The question is, do we find it in any real material? So we looked at the many, at this point, materials. So I'm going to show you two different systems with some examples. The first one is Strontium Ruthenate, where we can actually link the odd frequency pairing to the measured Kerr effect in this material. So let me show you how that can be done. So Strontium Ruthenate is this very interesting material. It's kind of layer like the cuprates, but it has strontium ruthenate instead of copper oxide layers. It's interesting here because it has 3 ruthenium 4D orbitals forming the Fermi surface in the normal state. So you have the XY orbital form the gamma-like band, and the XZ and YZ form a beta and an alpha-like band. And here you can already see here that I start with 3 orbitals, and they hybridize clearly in this case. So one can imagine, this interband hybridization I need is indeed going to come from just having 3 orbitals here that mixes. So this material is it's a low temperature superconductor. It's very likely non-S-wave state, disorder sensitive. It was believed for many years to be a spin triplet Kerr P-wave superconductor, but more recent results have shown that that's probably not what's happened. I write a question mark here because I don't know if it's fully established exactly what symmetry is. What I'm going to show you is not dependent actually of spin singlet and spin triplet. The only thing that matters is that it's breaking time reversal symmetry, which is measured, has been measured by the Kerr effect. So the Kerr effect is what happens when you measure the reflected light coming out from a material that breaks time reversal symmetry, and the reflected light is going to have slightly rotated plane of polarization if you have, well, in normal case, you have a magnetism in the material. So you measure this, and this was measured a number of years ago in Strontium Ruthenate. So this is the resistivity data coming down and showing the superconducting position here, and there. Then measuring this Kerr rotation through rotation of this reflected light, it picks up exactly at the phase transition and goes up here. And you note that this is nanoradians, so it's small, but clearly seemingly non-zero here in the superconducting phase. So it really looks like the superconductor state is breaking time reversal symmetry in this material. And that was seen as a good proof that this was a chiral state. But it turns out if you start with a single band superconductor, no matter how much time reversal symmetry it breaks, no matter how chiral it is, you will actually have 0 Kerr effect. Because to get the Kerr effect, it's reasonably complicated. So I'm just going to show you, I'm just going to tell you, and you have to go read the reference if you're interested in the details. You need to actually have an interband pairing in the material that has a relative superconducting phase to get a finite Kerr effect. And it has to do because you need to have a finite transverse Hall current response. And to get that, you actually have to have multiple bands involved. And now you can maybe already see here, but this interband pairing is exactly what I need for the odd frequency state. So when we discovered that this existed, this material that has a measured Kerr effect, that seemed to only be there with interband pairing, we got very excited. So we started looking at this, could we link these two with each other? So we said, okay, let's first do a very simple 2 orbital model. So I'm going to ignore one of the ruthenium orbitals. So say, let's just look at the alpha and beta bands here. And I'm going to assume I have a spin triplet pairing, but everything I'm going to say actually works for spin singlet pairing too. So I do this, and I do it extremely general. Okay, I have 2 bands, so they have some interorbital energy. I have some interorbital hybridization. I have some intra-orbital pairing. I have some interorbital pairing. So all terms here can be non-zero. And then I just derive what is the odd interorbital pairing. So I take F12 minus F21, and I get these terms. So you clearly see it's odd in frequency as we would expect. We get one term that comes because you have a gap asymmetry. So delta 2 is not equal to delta 1, and the interorbital hybridization. This was a term I talked about before. Then I call this term gamma, but here I call it epsilon 1, 2. But I could also start with actually, if I have an interorbital pairing, I only need a dispersion asymmetry, which I of course have because I'm considering 2 different bands, so starting with 2 different orbitals. So this is always non-zero. Now, if you look at earlier results published for the Kerr effect, it actually turns out that to get a finite Kerr effect, you need to have interorbital hybridization and a gap asymmetry. So this imaginary project here needs to be non-zero, or you need to have an asymmetry. You need to have interorbital pairs, so delta 1, 2 is non-zero, and you have to have an orbital asymmetry. So this prefactor here is non-equal. It's not equal to this prefactor. And these are exactly the same conditions. So whenever, well, it's not exactly the same equation, but if you stare at this long enough, you realize that if this is non-zero, if you measure an intrinsic Kerr effect, then you will always have this term being non-zero. So by measuring intrinsic Kerr effect, we know that there's odd frequency superconductivity in this material. That was a 2-orbital model. You might say, okay, what happens if I have 3 orbital models? And you can work out even an odd combination of the orbitals. And I'm just going to show you the numerical results, but this shows the 3 different orbitals here for a specific combination of parameters. But nonetheless, it works for all combinations, as long as you end up with some mixing between the orbitals or interband pairing. And here, this is the odd component, and it's small. I had to multiply this by 100 to see it in the same scale. But the Kerr effect is also small. It's measured in nanoradians, so it's a small component in this material, but nonetheless, it's there. And here I start with a chiral p wave, and the odd frequency is also going to have a chiral p wave symmetry. So this shows that the Strontium Ruthenate, you will have some odd frequency. It's not a lot, but it's there, and it's there. And you know it's there because you have a finite Kerr effect. Okay, so that moves me into the last topic. So here I want to start with a completely conventional superconductor. So I don't start with a multiband structure, but I'm going to drive it with light. And I'm going to show you that due to this driven system, we're actually going to get odd frequency pairing anyway. So let's start with a conventional superconductor, SY spin-singlet. I drive it with circular polarized light. It could be linear polarized too, but the equation I'm going to show is for circular polarized light. And this is a periodic drive. We can use Floquet theory. So we have a vector potential A. Let's just have some frequency dependence here and some amplitude. And it turns out you can model this system with a system that doesn't depend on time, but the price you pay is that you get copies of your system. So this is original copies, and then you have what could be called Floquet sidebands, where you have the same Hamiltonian, but shifted by the drive frequency. And all the system coupled by this operator U here that you see depends on the amplitude of the field. And this factor here is because it's circular polarized light, but it could also have other forms if it's linear polarized. So here you might again see where I'm going. I get bands, I get multiple bands in the system, but they're entirely generated by light here. They are not there if I don't drive the system. So the question is, of course, does what I've talked about in the multiband setting work for these Floquet bands still? So we start looking into that and said, okay, what I do have is these pair amplitudes. They depend on the 2 spins. It depends on momentum and also time, generally T1 and T2 for the 2 electrons pairing. And I can, in the Floquet picture, I would be interested in looking at the Floquet pair amplitude, where I have transformed into the Floquet bands. So N and M would either be, this is the 0, 0. This is N equal to 0, but I can also have N equal to +1, +2, and so on. So this is a Floquet pair amplitude, and it turns out that to see which is even and odd here, it's a little bit different due to this prefactor here. But if you change all the indices around, you end up with a minus sign, but you end up not just exchanging N and M, but you also pick up a minus sign here. So that's a different from what I talked about before in multibands, is the N and M goes to minus M and N. And M and N can also be negative because you have an infinite amount of negative M and N sidebands. So in total, you get a whole cadre of possible combination of symmetries, but the one I'm going to look at here is this. So I have a spin-singlet S-wave state. It can be even in frequency, and then it's even in Floquet index. But I can also have the spin-singlet even in S-wave state that is odd in frequency and odd in this Floquet index. And now being odd in Floquet index means N goes to minus M and M goes to minus N. So it's a difference. So let's just see if this works. So now I'm going to look at pairing that is even and odd. So plus is even in this Floquet index, minus is the odd one. So I combine them in this way. And I looked just at intra pairing. So I'm going to pair with electrons sitting in, in the 1, 0, 0 plane, or the 1, 1. So both electrons on the same plane. So to first order expansion, beyond, where I include one term of this transformation between the two, between the sidebands, I get these results. And it turns out that pairing within this 1, 1, well, it could also be -1, -1, is actually odd in frequency. Sorry. So I have both a term that is actually just depending on the drive frequency, and then I have a term to second order here. And the second order process you can think of as pairing. Well, you start pairing in the one sideband. You have one electron scattering by emitting a photon down to the 0 sideband, propagating a little bit there, and go back to the 1 sideband by absorbing a photon. So this is the second order process as seen by the second order term here. But it also has the first order process where everything happens within one band here. I can also have inter-sideband Floquet pairing. So again, I'm going to form this combination for the even and odd. So now I'm going to pair between different sidebands. So for example, I pair between 1 and -1. So that is this one, or I pair between 1, 0 and 1. So that will be this one here. And here you pick up to lowest order, you pick up this 0 and 1 is actually odd in frequency. I see that with the omega here. It's actually even in the Floquet index, indicated by this plus sign. And how does that work? Well, it's actually odd in the momentum here. And you see that this UK was actually a linear in K. So this is actually an odd frequency, even Floquet sideband pairing, but it's P-wave and spin-singlet. The spin index here is suppressed because it was spin-singlet. And this process, how can you think about this process? Well, it's pairing between the two bands. The first order is simply saying, I'm going to take this electron, propagating, absorb a photon. That's what this UK does. And then here, so that's this pairing here is a pairing that happens because you absorb a photon. And you also have some second order processes here as well, where you emit 2 photons, for example. So that was to lowest order. We can do this to, well, we can numerically sum to very high order and make sure it's converged. So here I'm just plot the resulting Floquet pair amplitude. So this is even, the even in Floquet index, even in frequency, even in momentum. And this is how it looks if you plot this function of frequency and momentum. And then you have the ones that's odd in frequencies, odd in Floquet. And you see, they do overlap a fair amount, but what's interesting, especially up here at one multiple of the drive frequency, you have a lot of odd frequency. And that's actually here, you have very little even frequency exactly at this point. So you get dominating odd frequency, you get odd frequency pair dominating at the drive frequency, or at, I should say, multiples of the drive frequency in the system. Okay, so I think that actually summarizes what I want to say about multiband systems. So this is really where what's important is that you have multiple bands or orbitals, and you always have odd frequency pairing in the system as soon as you have some sort of process that takes you between your orbitals and bands. You can either have hybridization in a normal state or pairing that goes between the two orbitals. I'll show you what happens in Strontium Ruthenate. We've done similar work, it's calculated for uranium, platinum 3. In both cases, you can measure by the Kerr effect. I'll show you here an example of what happens in light-driven conventional superconductors. You can extend this and say, okay, well, this orbital banding that we're talking about, it could really be a layer index. So you have a bilayer system. You can have 2 wires where you get inter-wire pairing, or 2 quantum dots, or 2 valleys in reciprocal space. Even shown that you can apply this to pair density waves in cuprates, and you get odd frequency states there. So this is a reasonably generic way to think about how you can generate odd frequency pairing by having this additional index for your Cooper pair. So with that, I just like to summarize what I tried to tell you today a little bit about, and that is odd frequency pair correlations. They are measured. They are effectively saying I'm going to have an internal time difference in my Cooper pair. And if that time difference is odd in frequency, well, then I have odd frequency correlations. It's well established in SF structures. I showed you that if you instead have a very nodal loop semimetal between my two contacts, actually get very good Josephson effect, only driven by odd frequency pairs. And then I moved to multiband system, where you can think of this as a spot -1. So all this similar spin, parity, orbital, and time needs to combine to -1. And that means that, for example, it can be odd in time if you have an odd interorbital pairing. And this ubiquitous system, which has some interorbital band wire, dot wire valley, and so on processes. And it exists in Strontium Ruthenate, as far as we know. And also you can find it by driving conventional superconductors. So with that, I thank you for your attention, and I'm happy to answer any questions.
Thank you very much, Annica. So we have time for questions.
Can I maybe ask a question? I have, if you allow me, I have a question, maybe even objection about one of the models you used, about this model of nodal loop semimetal. Can you maybe show this slide when you introduce this one? It's easier to explain what I mean.
Mm-hmm. Sorry, I think it's here. There.
No, just still further on, just a very introduction of this notion of nodal loop. Yeah, no,
yeah.
Even one more.
There.
Yeah, this one.
Okay.
Yeah, okay. This one, bottom right. That's actually a situation when you have two overlapping bands, and you have Fermi surface. In one band, you have a certain number of electrons, and in another band, you have equal number of holes. That's actually electron and hole Fermi surface, two bands, conduction band and valence band. With coinciding Fermi surfaces, this situation is known to be absolutely unstable with respect to what people call excitonic insulator, equal number of electrons and holes. And if you don't take this interaction into account, that's fine, that may be stable solution. But as soon as you introduce electron-hole interaction, Coulomb interaction, and so on, then this state is absolutely unstable with respect to opening of the gap. That's what people call excitonic insulator. Now, people usually argue that, okay, maybe this nodal loop, this symmetry protected. It may be fine if symmetry is symmetry, but this electron-hole pairing, excitonic pairing, can easily really break this symmetry. People usually, when people consider nodal loop semimetals, practically never checked whether the state is stable. And my claim is that it's theoretically, at least, it should be always unstable with respect to opening of the gap and removing of these nodal line semimetals. So the very notion of nodal line semimetals, at least in this simple model, I think it's simply wrong.
Yeah, I mean, exactly as you say. So the same way as the nodal, so the veil point is symmetry protected. The loop is also symmetry protected. Of course, if you have some interaction that breaks that symmetry of the crystal,
yeah, there may be electron-hole pairing which breaks the symmetry.
But
that will be always the case. It will be always unstable if you simply treat it in a simple kind of treatment like BCS. Then you sum electron-hole bubbles, and that will be logarithmic divergence. That will be mathematically exactly equivalent to BCS theory. It will be absolutely unstable, always.
Yeah, what I can say, and it's not, there are materials where I believe this has been measured at this point at the sea. It might be that it's, the question is how degenerate it is. It can be a direct loop material too, but it has, as far as I know, been measured in some materials where you see a loop or lines in a Fermi surface. So yeah, maybe that's.
I always had problems with these claims, actually.
But I think it was down to the crystalline protection. I mean, there is a symmetry protection of the.
Yeah, but people never checked whether symmetry will survive interactions. whether there will be spontaneous symmetry breaking. That my claim that there will be always, practically always, theoretically at least, there will be electron hole pairing which will remove the symmetry protection. This will be spontaneous symmetry breaking, which removes the symmetry protection.
Yeah, I mean, if you have some interaction breaks the symmetry, then yes, you can open again.
And that's, as I said, actually, electron hole pairing is always unstable, it's logarithmically divergent. And mathematically, it's always, it should be always the case. That's my point.
Yeah, thanks.
Okay, good.
We have questions by Gersh and David. Maybe Gersh can unmute himself.
Yeah, this is Gersh. I have, thank you, first of all, thank you for a very interesting talk. I have a practical question in relation to Strontium Ruthenate that you, and it looks like you have some detailed backup on your claims and calculations. The spontaneous Kerr effect that you refer was measured at 1.5 microns, so really very far. Now, if the claim by Teller and Carlin and related papers is correct, and you basically reproduce that the interband scattering is the one that breaks the Galilean invariance, right? That's what you need here. Then did you or did anyone look on how would that magnitude of the Kerr effect depend on the frequency, whether you would expect enhancement of the frequency of that interband scattering, and what actually is the value if you, because looks like you have done numerics trying to fit the band structure, what is the interband scattering parameter where this type of resonance enhancement could be expected?
Well, let me first say, so this is really assuming it's an intrinsic Kerr effect. It could be that it's caused by disorder in the material, and what I've said is not. But
yeah, it could be impurity,
it
could be impurities, and other, there's a list of possibilities.
Yes, what we did, and sort of this was the 2-orbital model, but we also did with 3-orbital, but we did not have
but let's say it's 2, so for simplicity.
Yes, we did not have any frequency dependence here. We had momentum dependence on these, but no frequency dependence.
No, but the frequency dependence will come in when you calculate the Kerr effect. I would expect that there's going to be enhancement in your sigma in your sigma xy that you need there for the frequencies that are close to this off-diagonal hopping.
Well, the short answer is I don't have a good answer for you.
Okay.
We compared it only at this level. And, well, actually, there's another paper who did it for 3 orbitals, which we also compared. It was just simpler to present it for 2 orbitals. Right. But we didn't actually. We cheated a little bit. We used other people's result for the Kerr effect. Okay. So that's why I can't give you an answer on that, because we simply didn't look at that. But it's an interesting.
Okay, thank you. Maybe Annica, maybe we can. I can follow up. I'll write to you, and maybe.
No, I would be very interested in doing that. Yeah. So you're saying, okay, that sounds good.
Okay, thank you.
David, you're next. Cool, thank you. You are muted.
Can't hear anything. It doesn't look.
Yes, we cannot hear you. Nope. Maybe I can hear his question. He posted here on the chat. As far as I understand, one speaks about odd frequency correlations, but they do not explicitly appear in the Hamiltonian, but manifest in response functions. Would it be possible to have a pairing mechanism that would be that will lead to an odd frequency order parameter as a part of the Hamiltonian?
Yeah, so that's a really excellent question, and I was trying to say a little bit in the beginning when I listed the. Let's see if I can go back. There's a lot of slides here, but go quickly. A little bit here with the history. So there has been a fair amount of work on that. I am not maybe the expert to talk about this, but all of this works here is really trying to do it with an order parameter in the Hamiltonian. The ways you can definitely do it is by having, a composite condensate. So you have the Cooper pair, for example, and then you add another boson, and then you very reasonably simple get an odd frequency state. But there is some questions about, at least in some of this, and I think there's both papers that show that it works, and some people say it essentially a no-go on the stability, and it has to do with the Meissner effect becoming completely paramagnetic. So this is, to me, a very unresolved question. Is it possible? Well, it's possible to cook up models, but the question is, are they fundamentally stable, and could we find them somewhere? So that's why we have, and I would say we sort of have done the simpler thing. We're saying, okay, can we get odd frequency correlations in system? We don't have to worry about having superconductivity because we know it's there from just the standard Hamiltonian, and see how far we get there. But I think the result that show, especially in the multiband system, there's some systems, I didn't show you the result on that, but they looked at, for example, copper doped bismuth selenides. It's a dope topological insulator. It's an intrinsic superconductor. It's proposed to be an interband pairing mechanism. It has a lot of odd, in fact, the odd frequency is dominating in this material. And it turns out that the Meissner effect is actually not paramagnetic, but the odd frequency actually drives the diamagnetic Meissner effect. So I think to me, it could be a possibility to go to topological band structure, multiple bands that are topological, and then you can possibly get around this paramagnetic issue. So that could be a way forward to actually think about intrinsic odd frequency superconductors.
Thanks, Annica. Let's call for questions.
I have a question.
Sure.
Yeah, this is just a simple question. Are there applications of this type of states?
Yes, excellent question. They are. So the simple answer is yes. You wouldn't have superconductivity leaking into the ferromagnet if it wasn't odd frequency. So in that sense, Josephson effect in SFS structure is new to odd frequency. We couldn't understand, there's no way that it would exist if it wasn't for the odd frequency correlation. So in that sense, yes. Getting closer to actually measure the odd frequency, really get to the time dependence here, has been proving a lot harder and that's a little bit why I call it here, it was kind of hidden, but it becomes almost a hidden order because it has time dependency is sort of a relative time difference in the Cooper pair. So it's not obvious. Many properties you measure will sum over frequency. And if you sum over frequencies, the odd part drops out. So it shows up, as I said, for example, a Meissner effect sometimes, and so on. So there are, the paramagnetic Meissner effect, you can measure proximity effect. So in that sense, there are signatures, but few of them explicitly shows they're all consequences of the odd frequency. It's not, as far as I know, really measuring the odd frequency part. So I think that's big next step. I think that would be very interesting to see if we can really get closer to that time dependence. And that was part of the reason why we moved into this light-driven Floquet systems, because we're interested in see, okay, if we add a time dependence to the system, can we get closer to probing the time dependence? And it turned out we couldn't quite there. I mean, we discovered a lot of other interesting things, but I think it's an interesting avenue.
Thank you.
Okay, so I think with that we can thank Annica again. Thank you very much for being with us today. It was a very nice talk, very nice results, and the audience made it great for the discussion. So hope to see you all next week with the next quantum matter seminar.
Thank you so much.
Bye.